So this is the Analyzing Polynomial Function Notes. This is day 1. So X-intercepts. What is an X-intercept? What is an X-intercept? It's where the graph does what?
Intersects through the x-axis.
Where the graph intersects the x-axis. Up until now, I've been pretty lenient about you telling me the x-intercepts are at -5 or 3 or whatever. But from now on, beginning today and all the rest of the semester, x-intercepts have to be written in the form of a point, a coordinate pair, with the value of x, 0. So, having said that, what are the x-intercepts for this graph? And I'm going to call on somebody from each table. So up here on the right, front table, on the right. Tell me one of the x-intercepts that are in that graph. -2, 0. Good. Thank you, Jeremy. Okay, front table in the middle. Tell me another one. -1, 0. This table in the middle here. Tell me another. 1, 0. And over to the left, tell me 2, 0 is the last one. So from now on, all your x-intercepts will need to be written like this, as a coordinate pair with the x value, 0. So then, what is a y-intercept? Where the graph intersects the y-axis. And so from now on, those need to be written as a coordinate pair as 0, y, whatever the y value is. All right, so now I'm going to pick somebody. Dorian, what is the y-intercept for this graph? 0, 4, yes. Any questions so far? Okay, in this next part, the minimums and the maximums, we're going to talk about what a minimum is, but in polynomials we can have 2 different kinds of minimums and likewise 2 different kinds of maximums. A minimum for our discussion is the lowest point on the graph. But when we have polynomials like the one in this graph, we don't necessarily have just one lowest minimum. That's the lowest point and everything else is above it. In a parabola you do, in one that opens upwards. In an absolute value you do, but in these you don't necessarily. So a local minimum is a minimum, which is the lowest point on the graph, a minimum, within a defined region. And an absolute minimum is the only minimum. Or the one lowest point. And then we will write these as ordered pairs also. So this graph has 2 local minimums, one here and one here. Brittany, give me an estimate for one of those. Just give me an estimate for the one on the left. Negative 2, 2. I mean, I asked for an estimate. I think it's between 1 and 2. I think it's between negative 1 and negative 2. So maybe negative 1.5, negative 2. So I need to. Sorry. We've already done the X's. Oops, but we're still doing the minimums. Okay, sorry. I want to resume with the new picture. So we do not have an absolute minimum. There isn't one lowest point, but we have two local minimum, one at negative 1.5, negative 2, and then Oswald, do you have a question, Jimmy? Yeah, but give me just a minute to not be in the middle of this so I can sign you out. Oswaldo, give me an estimate for the other value, for the other minimum.
I'd say it's positive 1.5, 2.
Negative 2, right? Okay, thank you. Okay. In this next box, there are two typos. These two should say maximums. Local maximum. And absolute maximum. Sign Jimmy up. I need your badge, Jimmy. You understand about the new passes, right? You have to stay on this floor. So a maximum is the highest point on the graph. A local maximum is a maximum within a defined region. And the absolute maximum is I'm going to say the only maximum. I may have to change that, but we'll abbreviate it. So looking at the graph, Vanessa, would you tell me what the coordinates are for the local maximum in this graph? It's the same as the y-intercept. 0.4, yes. So that's local. Now look at the arrows at the top of this graph. Is it going to have an absolute maximum? No, because this graph is going to infinity. The y values are going to infinity, so there is no absolute maximum on this one. That's an NA. All All right, so as a definition of the domain, we want your domain, from now on, I want your domain in interval notation unless you're told to give it in as an inequality or set builder. The domain is all the x values in the function or graph. The range is all the y values. So what is the domain of this graph? I mean, you can't see it on the screen, but it's on your paper. Is it going to, does it look like it's going to get wider and wider and wider, albeit slowly, but forever and ever and ever?
So negative infinity to infinity.
Yes, so negative infinity to positive infinity. We already talked about where the lowest points on the graph are. Mariana, so what will the range be? It's going to start from the least and go to the greatest. What's the lowest y value? Because we looked at the minimum. What's the lowest y value? Mariana? That is the x value for that point. What's the y value for that point? -2. So our range is going to start at -2. With domain and range, if the point or the value is included, you must have a square bracket. Because it is touching, the value -2 is part of the graph. It's not an asymptote. You must have the square bracket or it's incorrect. Then with infinity, it's going up forever, so it's going to infinity. Anytime you have infinity, whether we're talking about domain and range or other kinds of intervals, with infinity, you must have a parentheses. With domain and range, you must have parentheses or square bracket as needed for the numbers. Okay, so now we're going to look at something that we haven't talked about before. So I'm going to give you definitions for an even function, an odd function. An even function is symmetrical across the y-axis. This means you could fold it in half on the y-axis and the two sides of the graph would match up. We also sometimes phrase it as y-axis symmetry. It is symmetrical across the y-axis or symmetrical with respect to the y-axis. Those are different ways you may see it worded. An odd function is symmetrical around or about the origin. So the origin is 0, 0, the point 0, 0, where the two axes cross. So if it's symmetrical about the origin, that means you can rotate it around the origin and it will match up at some point without going all the way around. Obviously, if you go all the way around, it'll match up. But it will match up at some point before going all the way around. Now, I need to give you two algebraic expressions for this. In y-axis symmetry, which is even, algebraically, f of x is equal to f of negative x. So think about a parabola with the vertex at the origin, the parent function. I know that 2 squared is 4 and -2 squared is 4. So f of 2 is equal to f of -2. That's y-axis symmetry. The odd function is f of negative x is equal to negative f of x. So basically this means a point in quadrant 1 is the same as a point in quadrant 3. So it is even. If you fold it on the y-axis, it matches up. It's symmetrical across the y-axis. So now I need to go up to the board and illustrate something. But apparently first I need to enter the attendance. So we're going to talk about, can I do this from here? We're going to talk about intervals where the function is increasing or decreasing. I understand that this is confusing to you until you get increasing and decreasing intervals in your head separate from end behavior. These two arrows mean that this function is going to go up forever and ever and ever. So if we're talking about end behavior, it's going up and it's getting wider forever and ever and ever. But that's end behavior. When we're talking about intervals where it's increasing and decreasing, we're talking about starting at the far left, way out at negative infinity, and as I move from left to right, what is the function doing? So as I'm moving from left to right, are these y values getting larger or smaller? The y values. They're going smaller. So the function is decreasing. The function, meaning the y values, are decreasing from negative infinity until we get to this lowest point right here, which we estimated it at negative 1.5. And then from negative 1.5, it turns. And so then what are the y values doing? They're increasing until we get to where? The y value is 4, but when we're talking about increasing and decreasing, we're talking about the x values. So till 0. Now, the reason we do that is the x values, if we're already saying the function is increasing, that's telling us what the y values are doing. Right? We know the y values are increasing. They're increasing until x gets to be 0. It's very common. A lot of people miss that. If I asked you where the interval is that it's increasing, a lot of people want to say it's 4. But it's the x value. The x value is the interval where it's increasing.
So then it would be decreasing getting to 1.
So then it will be what?
Decreasing when it goes to 1.
So then once x is 0, as soon as x is bigger than 0, yes, until not just 1, but all the way over here we think that's 1.5.
And then it will increase again at 2.
It'll increase from 1.5 to forever, infinity. Right? So don't use the intercept values. Use the lowest points and the highest points. So going back to our paper then, we need to give the increasing intervals. So starting at, the increasing intervals, the first one is at negative 1.5 up to 0. Then, somebody I haven't called on yet. Leo, where's the other increasing interval? The first one is from negative 1.5 to 0. Where's the next one? Yes. So, Christian, give me one of the decreasing intervals. Yes. Negative infinity to negative 1.5. And Alejandra, give me the other increasing interval. I mean decreasing interval, sorry. The other decreasing interval. What's the x value when it starts to go down again? Zero to 1.5, yes. Okay, so do you see that on the graph? That when x is 0, it's at a high point, and from there it starts decreasing until it gets to when x is 1.5. Okay, so now I need to talk a little bit about these endpoints. The mathematical world does not agree on what symbols to use when you're talking about increasing and decreasing intervals. The problem is that some people say, well, logically, when you get to that local minimum or local maximum, the point at which it's turning, it's neither decreasing nor increasing because it's changing direction. So they say, ladies, they say that since it's changing directions there, that you should use the parentheses because it is neither increasing nor decreasing at that point. But other people say, well, that point is part of the graph. We're not talking about an asymptote or something that it's approaching but not ever equal to. The function is actually equal to that. So they say you should use square brackets. So because this argument exists and nobody knows for sure, and at any point you may look at a textbook that has it one way or the other, the College Board for AP exams has decided that if it's a number, so we're talking about the negative 1.5 and the positive 1.5 and the 0. If it's a number, then that will be counted correct whether you use parentheses or square brackets. So this increasing interval could have been written as square bracket negative 1.5 to 0 square bracket union with square bracket 1.5 to infinity. But infinity is never there. I mean, you never reach it. So all infinity symbols must have a parentheses. So it could be either or for increasing and decreasing intervals. For domain and range, it can't be either one. It must be exactly the right one. But for increasing and decreasing intervals, it can be either one next to a number. Next to an infinity symbol, it still needs to be a parenthesis. So we did the work before we wrote the definition. Decreasing intervals, or that's where the function, or let's do it this way, where the y values, it is the x values where the y values are decreasing. And then increasing, that's the x values where the y values are increasing. It's where the function is increasing, but I thought it might help you to keep it straight if you thought of it as the y values.